Welcome to The Explainer. Today, we're pulling back the curtain on one of the most important, yet invisible technologies that powers our modern world. It's called adaptive modulation encoding, and honestly, it's the secret sauce that makes things like 5G and your home Wi-Fi fast and reliable. It's the unsung hero of wireless communication, so let's get into it.
So let me ask you a question. Have you ever been sitting on your couch streaming a movie and suddenly it starts to buffer? Or you're trying to load a web page and it's just crawling and you haven't moved an inch? Why is your connection so fast 1 minute and then so painfully slow the next? Well, I can tell you it is definitely not random. It's actually the fundamental challenge of all wireless communication. And once you understand this problem, you'll really appreciate the genius of the solution we're about to unpack. All right, here's our roadmap for today. We're going to start with the core problem, what engineers call the fading channel. Then we'll get into the elegant solution, the adaptive solution, and all the tools in its toolkit. After that, we'll dive into a real-world case study, adaptive MQAM, to see how it works in practice. Then we'll get real about the challenges, and finally, we'll wrap up with a massive payoff and see why all of this matters so much.
So let's kick things off with part one, the fading channel problem. You see, when a radio signal travels from a cell tower to your phone, it doesn't just travel in a straight line through empty space. The world is a messy place. The signal bounces off of everything: buildings, cars, trees, even people walking by. All these reflections of the signal arrive at your phone at slightly different times, and they interfere with each other. Sometimes they add up and make the signal stronger, and sometimes they cancel each other out, making it weaker. This constant, chaotic fluctuation in signal strength, that's what we call fading. Here's a great way to think about it. Imagine the wireless channel is the road your data is driving on. One moment, it's a perfectly clear 6-lane superhighway. You can put the pedal to the metal and send tons of data at top speed. But then, a thousandth of a second later, with no warning, that road can instantly become a winding, treacherous mountain pass in a thick fog. You'd have to slow right down to a crawl just to make sure you don't crash. That's exactly what your phone and the cell tower are dealing with, all day, every day. So, faced with that chaos, how do you build a reliable system? For decades, the old way of thinking was basically to assume the road was always that foggy mountain pass. You'd design the system for the worst-case scenario. And sure, it was reliable, but it was incredibly inefficient. Which brings us to part two, the adaptive solution. The core idea is so simple, but it's totally revolutionary. What if instead of just shouting into the storm and hoping your message gets through, the transmitter could first listen to the road conditions and then decide how fast to drive? And that really represents a massive shift in philosophy. The old way, on the left, was this one-size-fits-all approach. You pick one gear, one speed, and you just stick with it. It means you're wasting a massive opportunity whenever the channel is good. But the new way, the adaptive way, is intelligent. It's about being nimble. You measure the channel right now, you adjust your transmission to match it perfectly, and you squeeze every last drop of performance out of the airwaves that you possibly can. So how does this actually happen? Well, it all works in this really tight three-step loop. First, your phone, the receiver, is constantly measuring the quality of the channel. It's basically giving the road conditions a score. Step two, it sends that little score back to the cell tower, the transmitter, over a special little feedback channel. This is the crucial listening part. And finally, step three, the tower gets that score and instantly adjusts its transmission parameters for the very next piece of data it sends you. And this loop isn't happening once a minute. It's happening hundreds, sometimes even thousands of times every single second. Okay, so the cell tower gets this score. It knows how good the channel is. What can it actually do about it? This brings us to part three, what I like to call the adaptation toolkit. You can think of the transmitter as having this control panel with a bunch of different levers it can pull and knobs it can turn to fine-tune the signal. Let's take a look at the three main ones. The first, and maybe the most powerful lever, is variable rate. This is all about changing how much data you cram into each tiny piece of the signal. So when the channel is that beautiful, clear highway, you can use a really complex signal that packs in a ton of information. Think of it like sending a full 4K video stream. But the second the channel turns into that foggy road, you immediately switch to a much simpler, more robust signal that carries less data, kind of like sending a basic text message. The goal is to always be sending data at the fastest possible rate the channel can safely handle. All right, the next lever is variable power. This is pretty intuitive. It's just like adjusting the volume of your voice. If the room is quiet and the person you're talking to is close, you can whisper. If the room is noisy and they're across the room, you have to shout. The transmitter does the same thing. When the channel is clear, it can dial back the power to save energy.
When the channel is bad, it cranks up the power to blast through the noise. There's a really cool technique here called channel inversion, where the goal is to adjust the power so perfectly that the signal arrives at your phone at a constant, steady strength, no matter what chaos it went through to get there. And the third big tool in the kit is variable coding. Now, you may not know this, but all digital data has extra bits mixed in, called error correction codes. You can think of this like protective packaging. When you're shipping something sturdy, you might just put it in a simple box. But if you're shipping a fragile glass vase through a rough storm, you're going to wrap it in layers and layers of bubble wrap and stick it in a reinforced crate. That's variable coding. When the channel is good, you use a light code. When the channel is bad, you add a ton of that bubble wrap. It takes up more space, so your data rate goes down, but it dramatically improves the odds that your data arrives in one piece. So you can see here, there's no free lunch. Each of these techniques has a trade-off. Variable rate is all about maximizing your speed, but it means you need more complex hardware. Variable power gives you rock-solid performance, but it can chew through your phone's battery when the signal is weak. And variable coding makes your connection super robust, but all that extra packaging lowers your top speed. In the real world, systems like 5G and Wi-Fi are intelligently blending all three of these techniques moment by moment. Okay, so let's move on to part 4 and get into the real nuts and bolts. We're going to look at how this all comes together in a very specific and incredibly important technique called adaptive MQAM. This is really at the heart of how your devices achieve those blazing fast speeds we all want. So MQAM, which stands for Quadrature Amplitude Modulation, is a clever way to encode data. Imagine a two-dimensional graph. MQAM places points on that graph, and the position of each point represents a specific string of ones and zeros. A simple version might have just 4 points, and each point can represent 2 bits of data. But you can increase the density. 16 QAM has 16 points and carries 4 bits at a time. 64 QAM has 64 points and carries 6 bits. You get the idea. The more points in your constellation, the more data you can send. But there's a catch. The more points you have, the closer together they get, which makes them way more susceptible to noise. You can only use those super dense constellations when the channel is exceptionally good. Now, here's where things get really interesting. When researchers were first developing these ideas, they made a surprising discovery. They compared a super complex system that continuously varies both its rate and its power with a much simpler system. This simpler system, called truncated channel inversion, just picks one fixed data rate and turns the transmitter completely off when the channel gets too bad to support it. And what they found, as you can see here, is that the simpler system performs almost as well as the super complex one. That was a huge insight for engineers looking to build practical, cost-effective systems. You see, this idea of continuously adapting the rate, it's a beautiful mathematical concept, but it's just not practical to build in the real world. You can't design a chip that can create a constellation with, say, 42.7 points. It doesn't work that way. Real hardware needs to switch between a small, predefined set of modes. And this practical approach is called discrete rate adaptation. And this is exactly how it works. Engineers carefully define different thresholds for channel quality. As you can see in the table, if the channel is really, really bad, the system just gives up and doesn't transmit anything. It's better to send nothing than to send garbage. But if the quality improves a little, it'll start with a super robust but slow mode, like BPSK. As the channel gets clearer, it starts climbing the ladder, stepping up to QPSK, then to 16 QAM, and when the channel is absolutely pristine, it'll jump all the way up to 64 QAM or even higher. Your phone is constantly hopping up and down this ladder to perfectly match the road conditions of the moment. So what's the cost of taking this practical shortcut? How much performance do we actually lose by using just a handful of discrete steps instead of that perfect theoretical continuous adaptation? Well, the answer is amazingly little. As this chart illustrates, it turns out that with just 5 or 6 different modulation modes to choose from, you can get performance that is within 95% of the absolute theoretical maximum. I mean, that is a phenomenal engineering trade-off. It's what makes this whole concept not just possible, but incredibly effective in the real world. Okay, this all sounds pretty incredible, I know. But it's not magic, and it's certainly not without its own set of very difficult challenges. So for part 5, let's talk about the real-world problems that keep wireless engineers up at night. The 2 absolute biggest hurdles are, 1, errors in estimating the channel, and 2, something even more difficult to deal with, feedback delay. And that delay is the real killer. Remember that 3-step loop: measure, send feedback, then adapt. Well, that whole process takes time. It might only be a few milliseconds, but in the world of wireless, a millisecond is a long time.
By the time the transmitter gets the report from your phone and adjusts its signal, the channel has already changed. As the quote says, the transmitter is perfectly adapting to a channel that doesn't exist anymore. It's like trying to drive a race car by only looking in the rearview mirror. You have a perfect view of the road you were on a split second ago, but that's not the road you're on right now. And the price you pay for that delay is errors. A lot of them. This chart shows the direct relationship between how long the feedback delay is and the bit error rate, or BER. The longer that delay, the more stale the information is, and that means the transmitter is more likely to make the wrong call. Like, it might see a report of a great channel and switch to a complex high-speed mode right as the channel quality suddenly tanks. That mismatch between the signal and the channel just creates a cascade of errors. Minimizing this delay is a genuine obsession for the people who design these systems. Which finally brings us to our last section, the payoff. Because despite all these tough challenges, the complexity, the delay, the estimation errors, the benefits of being adaptive are so ridiculously huge that they completely revolutionized wireless communication. So let's get down to the bottom line. Just how much better is it? Here is the number you need to remember, 10 times. In typical wireless conditions, a modern adaptive system can be more than 10 times more spectrally efficient than an old-fashioned, non-adaptive, fixed-rate system. That means 10 times more data can be sent in the exact same amount of radio spectrum. That's 10 times more users on a network, or connection that feels 10 times faster. This isn't just a small, incremental improvement. It is a monumental leap. It is the core technology that enabled the entire mobile data revolution that we all now take for granted. And that leaves us with a really exciting question for the future. You see, everything we've talked about today is about a system that reacts to the channel's past. But what if it could predict its future? With the explosion of AI and machine learning, the next generation of wireless technology, 6G and beyond, might be able to learn the complex patterns of a wireless channel and adapt not to where the channel was, but to where it's going to be in the next millisecond. I mean, just think about how much smarter and faster our connections could get then. And that's our deep dive on adaptive modulation and coding. If you enjoyed this explainer and you want to keep digging into the incredible technologies that shape our world, please do subscribe to the channel. If you found this useful, hitting that like button really helps us out. And of course, if you have any questions or if there's a complex topic you want us to break down next, please drop it in the comments below. We read all of them. Thanks so much for watching.